How are you guys doing today? Good, perfect. All right, so we have an exam, obviously this Wednesday and Friday. You guys in Wednesday or Friday? Wednesday. Okay. So Friday. Okay. So the 7th and 9th in April. So this will be the another review session today. Okay. So also if you're watching this one too, I think I normally hold like a 2 or 3 review session right before the midterm exam. So you can always keep going back to your YouTube channel more precisely on those the last 3 or 2. That would be really great. Okay. So there's another review here. Okay. So let's try this one. Oh, yeah. Maybe try this one real quick. This is what we did for like a keto tautomerism, but it's slightly different from what we did last time. So we can talk about this. About maybe 1 minute. 1 minute. Okay. Yeah. So here's what we can do. So in here, it's slightly different from the mercury that we did last time. We're gonna put the hydrox group at the end, not in the middle. Okay. So in this time, and then because of the mechanism we didn't cover, which will be covered over 2. You're actually going to have a elimination of this 2 over there. Okay, so it was already applied there. Okay, so now this is a single bond, so you can actually have this one. Yeah. That's it. This is a simple trick. Unlike the mercury one, you can put the carbonyl group at the end if it's the terminal alkyne. So if you have a triple bond at the end, just try to put that on the end. Okay. So, does it make sense? Okay. Okay, so this is actually pretty, I think, simple one. So if you have these carbocation in the middle, which do you think will be more stable? You can put it in order. Maybe this is the most stable, this is the least stable, this is somewhat stable in between. But 1 minute. Okay, so here's the thing. If you have a cation are surrounded by more numbers of R, I can say some alkyl groups like in the carbons, anything, because of the induction and hyperconjugation, will be more stabilized. Even though this carbon now experiencing a very poor electron density right now. but because of the induction from the carbons and also hyperconjugation with the carbon-hydrogen bond along with this one, this might be quite well stabilized. I mean, it's still very unstable because it's carbon, but relatively speaking, this is the most stable. Okay, most stable. If you think about this one here, they don't have any R groups around this carbon, and hydrogen is not really good way to stabilize the carbocation part charge because it's also quite low in electronegativity. So this is the least stable. Okay. So if you have one R, two hydrogen, somewhat in between, so be the second, or you can say second stable or second least less stable. Okay. So 1, 2, 3 in order to making like more stable, least stable. Make sense, right? All right, let's go to the next one. Oh, okay, this is kind of a so you can try maybe 1 or 2 minutes. Okay, about 30 seconds. So, okay, we'll do this. Okay, so the Linde's catalyst is kind of like I mentioned before, it's kind of a weaker version of a regular reduction. So regularly, we can use the hydrogen over some catalyst with the palladium on charcoal or the carbon molecule. So if you do that, you can actually reduce your alkyne even to the alkane. But we sometimes use Linde's catalyst because we want to use until, we just want to reduce until the alkene, not the alkane. So this will actually make it all the way to be reduced, so be alkane with this one. But with the Linde's catalyst, it only starts at the alkene. Okay? The thing I want you to remember though, if it starts at the double bond, you need to know if it's going to be either cis or trans. So in this case, it is going to be cis. Okay? So those two are on the same side. So basically, it kind of makes sense because the way they approach to get the reduced to pick up the hydrogen, they're actually coming onto the same side on the metal catalyst. So this is how they pick up the hydrogen one by one, but they start to the alkene. So that is kind of a reason why they're actually going to show you the cis form over here. Okay? So let's try the other one. Okay? It will make more sense. Okay, we have maybe this one now, but we'll treat it a little bit differently this time. So you don't have to know the mechanism, but yeah, this will be another good example for reduction. But maybe 30 seconds. Okay, so this one, the way they work is once you have a carbanium with one of the pair of the pi electrons on these two carbons over here, lithium will give you one electron to here, and next time they give one more. So once they pick up this lone pair of this carbanium, they charge, or pick up the hydrogen from the ammonia, and this one later they get the electron twice. That makes once radical is pair of electron pick up the hydrogen on opposite side. So this will become, at this time, unlike the one we just did, will be trans. Okay, because you see the hydrogen are attached on the opposite sides. So this is very good, I think, example for reducing your compound only onto the one step down, but in a different form because it will stay as an alkene. So either you're going to put it in the cis or trans. There's two methods you can choose. This might be a good example probably you may see. Can I move on? Oh yeah.
So that one will always be trans? Like,
There is always trans.
and the other one will always be cis?
This is cis, yes. So the way they, so the one with the metal surface, the catalyst, they have to come on the same side, right? That's why they kind of force to those two Argus force on the same side. But this one, once they're making a carbon cation once on the one of the carbon in a double bond, they grab this one. By doing that, they also grab the hydrogen on the other side will be much easier. So yeah. Okay. Alrighty. Then okay, this might be also. Okay, so we're gonna treat this one with a very strong base, and with some halogenated methane, iron methane. Okay, so okay, here's the thing. The point here is you'll be able to see the actual structure will be really good. Okay. This is what it looks like, right? So you have implied hydrogen over here, but if it's treated with a very strong base, this base simply means what? They're going to accept the protons. So this is a really strong base. They try to capture this proton right here at the end. Okay. So if they capture the proton, meaning like they're not taking hydrogen whole, right? They're only taking proton, meaning the pair of electron right here goes to this one. Because they only take proton, not hydrogen, right? This is base. So this will be negative charge. Because so this is very high density right now. And then they can attack the one on the carbon. Because of this halogen, this might be relatively speaking quite electron poor, so they can attack this one. And so that way they can have a full part to take whole pair of electron to themselves, and they just leave. So what happens to this one, they make this one. Okay. So yeah. So you just attaching this one to right there. So that's it. Okay. All right. So the next one is I think it's not too hard. Can you guys name this one real quick? I think it's quite. Yeah. Okay, so you see this is 1, 2, 3, 4, 5, 6, 7. Okay, 7, right? So this might be the longest carbon chain. So I'm gonna put hat, and then this is all single bonds. So it's heptane. Okay. The thing is, you have bromo groups, chloro groups over here. So you're gonna count the carbon from left to the right or right to the left. It will be left to the right, because you have tie in this bromo and chloro groups. If you count the carbon from here, here will be just 2 and 2 over here. So in this case, we follow the alphabetical order to put it as a lower locate number. So it'll be 2 bromo, and then it will become 6, right? 6 chloro. Yeah, I think that's correct. All right, so the next one. Okay, so you can find out there's 4 compounds. And then try to find out strongest acid here among those 4. We could do this one as well. So the thing is, those carbons are in double and single bond alternating here, making an aromatic ring. This is one with just single bond. The one has the double bond and triple bond. So what might be the strongest acid over this 4? Okay, so here's the thing. If you think about the strongest acid compounds, you need to think about the compound that give us the lots of numbers of protons. So if they're willing to give us the proton, that makes that compound very strong acid here. If you look at those one here, this one has a double single here, and this is single double bond, the triple. So if you think about this one here, this one has the sp3, sp2, and this is sp. you have a lot of carbons is going to sp3, sp2 conjugation. So if you think about this one here, if you put the proportion of the s orbital character on here, this will be the highest one because it has only one s, the one p orbital character hybrid over here. So if you think about the s orbital, which is closer to your nucleus or nuclei on several atoms, and also it has a more strong power to hold the electron density to themselves. So think about when they lose the proton over here, okay? And then this might be the relatively speaking better to hold the like the electron density around this carbon here. So once they detach the proton from their form, if that is more stable, means it's better, a stronger acid, because they will not mind. This will be very this will be very unstable though, obviously. Like there's a formal charge in here, formal charge, after they donate the proton there. Even though they will be very unstable, but still, relatively speaking, this will be more stable among those four because of the strong bond inside in here. So they will try to keep this quite, relatively speaking, stable anion form after donating the hydrogen cation. So that's pretty much it. You don't have to know the pK value, but this will be obviously the lowest one. So that is the strongest one over here. This is almost similar. They are tied, and this is the least stable. Okay. So